gonna shade.
Shader's gonna shade,
yeah.
Shader's gonna shade, yeah.
Gonna shade.
Shader's gonna shade.
Gonna shade, yeah.
Gonna shade. Shader's gonna shade, yeah. Hey everybody, welcome to the third part of the GLSL Phong shader lightning tutorial. And in this one we are going to hopefully to finish this lightning shader. And what we miss is actually only the specular light, because we got the diffuse light and we also need the ambient light. Then we're going to add the specular light, and this is going to look a bit cooler in the end. So let's see what we got. We got a grid shape that has this shader applied, and we got a light that we can actually move, and this is a point light that illuminates the shapes with a diffuse light only at the moment. So as you can see, we can move the light, which is represented by this little other grid shape here. Change the color, and that's basically it. So let's see what we got inside the shader. Let's make a little recap. So I opened the shader that is inside the GGL shader object. I just opened it with Visual Studio, which is a text editor, and let's see what we got. So we got a couple of parameters. We got the position of the vertices in object space. We got the vertex color. We got the vertex normal. Then we got the model view projection matrix. These are all state parameters that we get inside the shader. So which means they are passed from the max application to the shader program. And the model view projection matrix we use to transform the object in screen space. This is what every shader must do. And then we got the model view matrix, which we use to transform the objects in camera space, which is the space where we do the lighting calculations. And then we got the lighting parameters, and then we pinned those parameters here. So we declare the parameters as uniform. So for example, the model view projection matrix, the model view matrix, then we calculate the normal matrix as the transpose of the inverse of 3 columns and 3 rows of the model view matrix. This we use to calculate the normals in camera space. Then we got as the input, so this is as input the vertex position, the vertex color, and the vertex normal. And then we got the structure of the light source parameters with basically all the attributes that we can modify from the light object, GGL light object. And this is basically an array, so we decide how many lights we want to have in this scene. And that must be also mirrored with object GGL lights inside the max patch. So at the moment we only got one, and we declare these structures inside this other structure, which is called lighting parameters. We declare basically an instance of these structures inside the lighting parameters uniform, which is a structure in itself actually. And then we got an output which we pass to the subsequent stage of the pipeline, so it's called JIT per vertex, and inside there is the light intensity calculation. So this is just in the end, this is just a vector for every vertex gets calculated the intensity of the light at that vertex, okay? And then we have the algorithm to calculate the light. So first we transform the vertices in I space, so we call it I position, by multiplying the vertices for the model view matrix and then taking a vector out of that, so only the x, y, and zeta components of the vector. Then we get the normals also in I space, and we normalize them because from the normals we actually just care about their position, so we normalize them. Then we get the position of the light in I space, which is just the position of the light. We don't need to multiply it by the model view matrix because the light position comes already in I space. And then we get a vector that goes from the shape to the light. Let me actually get this little drawing that we made last time. Exactly, so we get a vector that goes from the shape to the light, which is this vector here with a green arrow, let's say. And this we do simply by subtracting the light position from the vertex position. So subtracting the vertex position from the light position. So we get a vector that goes from the vertex to the light. And then we get a vector that goes from the shape to the camera, which is basically just normalize and negate the position of the vertex itself. So then we get the vectors that go from the light to shape. So we simply reverse this green arrow. We just reverse it. So we got this vector that goes from the light to the shape, this red arrow. And then we get a reflect vector, and this is, we didn't use last time, we already calculated it, but we didn't use it last time. This we are going to use in the specular light calculation. Okay, so this is the vector, basically this is orange vector here. That is the reflection, the reflected vector of the light in respect to the normal, which is this black vector here. Okay, so then we get, the dot product of this, of these two vectors, since they are both normalized, is basically the cosine of the angle between them, and this gives us the intensity of the diffuse light at that vertex. Okay, it's pretty simple. And then we do the max between this and 0 because we don't want negative values. If a value is negative, it means that the angle is greater than 90 degrees, because the cosine of an angle that is greater than 90 degrees is going to be negative, which means basically that the light is covered by the shape itself. Okay, so then we calculate the diffuse light by multiplying the light diffuse parameter, which is basically the diffuse parameter we set for the light here, and then we multiply this by the dot product. Okay, then we calculate it here, so we get the diffuse intensity, and then we pass it simply. We multiply it by the vertex color, and we pass it to the fragment shader, where we just use this as the color of our fragments. Okay, so pretty cool. Let's now complete this shader and go on with the specular light. Okay, so what we need to do now, so after we calculate the diffuse light, is create a float value, which is going to be the specular intensity. So let's initialize it with a value of 0, and then let's say if the shape to light dot normal is greater than 0.0, so the light is basically not behind the shape, then what we do is to assign the specular value. Let's actually call it specular. Let's give it the full name. So specular, it's equal to, this is equal to the dot product of the reflected vector, so reflect back, and the vector that goes from the shape to the eye, so shape to eye vector. Okay, but as before, we want to take the maximum between this and 0, so we say max between that and 0.0. Okay, so let's see what happens when we just use it like that. So we can simply do that. We can say specular, or let's actually call this specular amount. So specular amount, and then let's call this, let's create a vector and call it specular. This is actually the color of the specular light in itself, and we can use this as the light 0 dot specular, so the specular color of the light, multiply that by our specular amount. Okay, so then we can simply sum that to the light intensity, so plus specular. Okay, so let's see what happens. Oh, cool. We got our specular light. Now, as you can see, it's pretty massive. It's like a big white halo on the shape. And to make it kind of bigger or smaller, we can make the power of this value and elevate this to some power. For example, let's elevate this to 16. As you can see, the specular eye light gets smaller. And this is actually the value that inside the object is called shininess. So it's the attribute shininess. In fact, if we go into the GL grid shape, it has a shininess attribute that we can actually use to modify the size of the specular light. Okay, so we could either pass a parameter and call it shininess and pass this to the shader, or we could, as we did for the light, we can actually declare a front material structure inside our shader and simply use the built-in attributes of the light. So let's go for this solution. So to do that, we do as we did for the light, we do something like this. First we create a structure, and let's call these material parameters, and then let's fill it with the attributes of the material. So for example, the emission value, the ambient value. So this is kind of the color of the different material attributes that we have for the object. So then we got as well the diffuse, and then we got the specular, so a bit like the light actually. And then we got the float shininess, which is the one we are precisely interested at the moment. So then, as for the light, we have to say something like layout, std140. Then we have to say uniform front material parameters. Alright, and this is a struct in itself, so inside we declare an instance of the object material parameters and we call it front material, simply as that. Okay, so then if we want to take the shininess parameter of the material, we can just replace this 16 here, whoops, with front material dot shininess. Okay, but this will work only if we set auto material in the object to 0. Okay, so let's see if this actually worked. Seems it doesn't work. Oh, sure, it doesn't work because we need first to actually declare it as a uniform. We cannot just declare it there. So as we did for the light, we have to create it as a parameter. So the parameter name, and this is going to be the name of the struct we declared here. So front material parameters. Front material parameters. Exactly state is going to be front material. This is the name that you have to write exactly like this. And then we can bind it to the vertex shader. So bind param front material parameters program is going to be the vertex program. And now I think we can use it. So let me check. Still doesn't seem to work. Okay, so found the error was not working because I wrote here like bombed instead of binned. This is why it was not working, and also it doesn't give you an error in this case. So it's a bit tricky with the GLSL syntax in Max. It's a bit tricky because it doesn't give you an error if you write something like bombed instead of binned, but the shader will not work. Okay, so now we can modify the shininess parameter simply using the shininess attribute of the object. Pretty neat. We can actually now also use the front material attributes to calculate the final color of our components, like the diffuse and the specular. For example, we are multiplying the light specular color plus the specular amount of the light, but we can also multiply that by the front material specular parameter. So front material specular. Okay, which is basically, if we go here in the object and we say mat specular, this is this value here. Okay, so we can now use all the attributes like if it was a normal shader from like when we write lighting enable. Okay, we can also change the color. It's pretty neat. Then let's see what else can we do. Also with the diffuse light, we can multiply that, of course, by front material dot diffuse. Actually, in this case, we can also not use the vertex color, for example, or maybe, yeah, let's just keep it there. But we can basically replace the vertex color with front material diffuse. So if we go into matte diffuse, we can change the color of our shape. Yeah. The shininess, we can choose how big is going to be the specular amount. We can choose, for example, the color of the specular amount. So math specular, let's make it completely white, for example. We can kind of start to define better the material of our shape. Pretty nice. Alright, we can calculate now also the ambient light. So let's go under specular here. Let's create another bracket for it, call it ambient. And this is going to be the amount of the light, the ambient light of the light. So light.ambient plus, now multiplied by the front material ambient parameter. So the ambient light is kind of a light that is always there. So we can just sum it to the light intensity components. Cool. So if we go now here and we choose, let's actually put the shininess next to the specular since they're related, and then here let's take the matte ambient value so we can make it smaller or bigger. But then we also, this is multiplied by the light ambient, so we have also to go here in the light, and the ambient, as you can see, is set to 0. So if we set this to something like 1, it's going to be completely white, and so on. So the ambient light is kind of a light that is going to be summed to everything else. So I think we can do this in a way that it looks a bit better and just not sum to the rest. But for the moment, let's not apply it at all, let's keep it to 0. Okay, so we can actually just also hard-code these attributes inside the object itself. So matte ambient 0, 0, 0, 0, 0, 0, 1, for example, yeah. Okay. Oops, when I went down, this was matte ambient, okay. Cool. Matte specular we can set to 1. So we can hard-code it inside the object, so matte specular 1, 1, 1, 1. Okay, cool. Okay, nice. So the ambient we calculated, the specular we calculated, the diffuse we calculated. Maybe let's put them all together. So diffuse, specular, and ambient. Okay, cool. So the diffuse is the result of the diffuse light multiplied by the cosine of the light and the normal. And the front material diffuse. The specular is the specular light multiplied by the amount of specular light we calculate using, again, the dot product and elevating it to a certain power, multiplied by the front material specular, and the ambient light is simply the result of the light ambient multiplied by the front material ambient. And then we sum basically the vertex color by the diffuse, and then we sum it, we multiply the vertex color with the diffuse, and then we sum the specular and the ambient to that. Cool. One thing, since this is actually a point light, we could make it in a way that the farther the light it is, the smaller is the contribution of the light to the color of the object, right? So we can do that in a simple way. We simply have to calculate the distance between the light and the vertices. So we can do this, maybe let's do this here. So it's going to be a float. Light distance, it's equal to basically the length of the light position in camera space. So I light position minus the vertex position, so I position. Very simple. So we can do something like this. Basically we put vertex, diffuse, and specular, and we multiply this by, so let's create actually a float variable here. Let's call it dimmer, and this is going to be 1.0 divided the square of the light distance. So light dist multiplied by light dist. So let's see what we get if we use these as a value. So the diffuse and the specular multiplied by dimmer. So let's see. So if we make the light go farther, the shape is not lighted anymore. Okay, so it works pretty nicely. One last thing that we can add to this patch is to make the light moving around automatically around the shape. So in order to do that, we can do something like this. Let's pack the position inside the sub patch. Let's go inside. And we can use, for example, some noise numbers to get the position to be automatically updated. So we can create an object like JIT-BFG, give it basis like noise simplex. And this is going to be a 3, float 32, and actually we just need one single cell, but we need at least to give it 2 cells, so 2, 2, 1. Exactly, because otherwise the object will not work. So then we can receive the metro here and create a counter. Divide this counter for a certain number, so which will be basically the speed at which the light moves. Then we can use these as an offset for the third dimension, so 0, $1. And basically we can also send a bang to the object after we send the offset. Cool. Then we can use a matrix just to get one single cell from that, which is all what we need. So 3 float 32 1 adapt 0. Then we create a JIT gen in which we normalize this vector that we receive in entrance. So it's just going to move in around a sphere basically, if we normalize it, because the length of this vector is always going to be 1, so it's always going to be around the sphere, around our shape. Let's maybe multiply it by 3 or something. Okay, and then we can use JIT ether to get the matrix into a list. And then we can basically attach this. So let's take a look at what we get. Okay, we get a bunch of random numbers that we can get used as the position of our light around the shape. So let's see. Okay, this is pretty much working. But the only problem if we normalize it is that then the light is always going to be constant. And we're not going to see the benefit of using the light distance, because the light is always going to be around our shape. So maybe instead of normalizing it, what we can do is not normalize it. Not multiplying it either. But in this way the light sometimes will be inside our shape, which is not something we want actually at all. So let's maybe normalize it, multiply by 3. And then we can maybe do something like this. No. Let's maybe create a mat4. Let's create also this as a mat4. And then we can say basically the fourth value. So we can use ears width x, y, zeta. And then we can use the fourth value as maybe the absolute value of that plus a certain number, like in order to be away from the sphere, like 1. Then we can basically multiply that for that. Let's see if this works. Okay, so the light goes away. Okay, let's multiply this by something smaller, like 0.5 or something. Okay. Let's maybe sum it also plus 0.5. So the light sometimes will be closer, sometimes will be farther to our sphere. Cool. Then let's maybe just say, so now we get a list with 4 numbers inside. And yeah, they are basically going to be unpacked automatically, but let's just make an unpack FFF. And let's unpack them on their places, corresponding places. Okay, cool. Cool, this is a bit better, because now the light is also going to go closer or farther to our shape, right? Yeah, okay, nice. We can also create another object. We can create as many as we want, so let's actually copy this sphere here, and let's give it a shape like a cube, and let's position it below this sphere. So position 0, -1, 0, let's say -2 actually. Okay, and let's maybe scale it in a different way. So scale 3, 0.51. See what we get. Then let's say 3, 3, 1. Oh no. Let's say it's 3, 0.53. Okay, cool. So we get kind of a floor. It's a bit too fat. So let's say 0.2. Let's bring it back to let's bring it up to -1.3 or something. Cool. Now we got our floor. And we can also make it in a way that the light never goes below the floor. First we can also change the color of this fella. Let's maybe make it blue. So we can make it in a way that the light never goes too far from the floor. First of all, let's hard code this color 0.00361. So color matte diffuse 0.311. Okay, cool. Okay, so let's make it in a way that the light never goes under the floor. Let's write position light. And so we can simply do like this. We can create a vector here. And let's switch the x, y, and the zeta value. Okay. So, and let's say, for example, clip the y between, what is that? -1.3. So clip between -1.3 and I don't know, whatever, 10. So actually, let's clip it between -1 and this number here, and then z, we just pass it like it is. And now the light should never go below the floor, exactly. So let's maybe clip it even a bit more high, so -0.8 or something. Cool, so the light will never go below the floor now. Very nice, pretty nice, actually. This is actually pretty nice. Maybe not send it too far with that, so let's multiply it by 2.4, exactly. And nice, so this is it. This is our Phong lighting shader. It's actually kind of finished. And in the next videos we're going to see how to apply a texture, for example, to these objects. And then we're going to see how to do some other cool stuff with shaders inside Max and the GL3 package. Okay, so hope you liked the video. And if you like it, you can also subscribe to the channel, like the video as well. And you can, of course, download the patch for free on my Patreon. And if you decide to subscribe to my Patreon, you can also download another bunch, actually a lot of other patches for the visuals. Okay, thank you for following and see you in the next video. Wish you a good evening from Amazing Max Stuff. Ciao.
Shade, yeah.